In this video, we're going to talk about the idea of parametrizing a curve. So imagine that we've got a curve in either 2D or 3D. So the x and y coordinates are changing as we run along this curve. And if we're in 3D, then the z coordinates are changing as well. And the idea of parametrizing a curve means to describe all the points along this curve just using a single variable. And that's exactly what we need to do when we compute line integrals. So we're going to do 3 examples here to get some practice parametrizing curves in a few different contexts. So let's say for part A, the curve that we're trying to parameterize is a line segment. When we say line segment, we mean straight line segment between 2 points in 3D. Let's say we're going from point 1, 2, 3 to the point 7, negative 6, 5. So I'll draw a rough picture here in 3D just so we can visualize that. So the point 1, 2, 3 might be somewhere about there, and the point 7, negative 6, 5 might be sitting somewhere, let's say over here. And we're just trying to describe this line segment that goes from here to here using a single variable called the parameter. So here's how I would approach this. I would look at our x variables first, and I would say, well, our x coordinate starts at 1 and finishes at 7. So what's important here is that it starts at 1 and increases by 6. So meaning over the course of the line segment, we gain 6 units in the x direction. So let's do a similar kind of description for y and z. Y starts at 2 and decreases by 8. So you could say negative 6 minus 2 gives us negative 8. So that tells us we're decreasing by 8. And for z, we are starting at 3. And if you want to think about the net change in z, you could say 5 minus 3 is 2. So that tells us that we're increasing by 2. So if we wanted to describe this using a parameter, we could say x equals 1 plus 6t, as t ranges from 0 to 1. So that would capture our starting point corresponding to t equals 0. When we plug t equals 0 in here, we just get 1, which is our starting point. And then our end point would correspond to t equal 1. So by the time we plug t equal 1 in here, we get 1 plus the 6 units of increase to take us up to x equals 7. So in a similar way, we could say y equals 2 minus 8t. So this is negative because we're seeing a decrease of 8. And z equal 3 plus 2t. So by letting our parameter range between 0 and 1, and by recording our starting values and the amount of change that we're seeing in each variable, multiplying that change by our parameter, we're able to capture all the points along that line segment. So visually what's happening is this point here is the point t equals 0. Our endpoint is corresponding to the point where t equal 1. And as we run through all the real numbers between 0 and 1, we're capturing all these different points on that straight line segment. So notice that we've been able to describe a line segment which is moving in 3D just using a single variable, which we're calling our parameter. Right, now we're interested in describing the parabola y equal x squared plus 1, just over a certain section of x values. So let's make a quick sketch here. So this parabola here has y-intercept of 1. Let's just draw a rough picture and say our parabola as a whole looks like that. We're interested in just capturing the portion where x ranges between 1 and 3. So if I just highlight that in red, that would be this portion of the parabola here. Well, whenever you have a curve in the form y equals a function of x, an easy parameterization to choose is just to say x equal t, and then y equal whatever our function of x is. Just replace the x with a t to get everything in the language of t. So our x values are being recorded by the parameter t, and therefore our y values are being recorded by this function here, with x evaluated at t. So in other words, y equal t squared plus 1. And then the values for our parameter would just be whatever x values we were ranging through in the problem. So t would be ranging between 1 and 3. And that would capture all these points along the red portion of the parabola. A third type of parameterization that comes up when we're talking about line integrals is when we're dealing with part of a circle. So let's say that we're dealing with the part of the circle x squared plus y squared equal 9 in the second quadrant. So this is a circle of radius 3, centered at the origin. And we're just trying to capture the portion of this circle that lies in the second quadrant. So we're trying to come up with a way of describing all these different points here, but using just a single parameter. Well, let's flash back to polar coordinates for a second. Polar coordinates said x equals r cos theta and y equals r sine theta. But if we're working on a circle of a fixed radius, then we don't really need the r here. We could say we know our radius is 3, so we can write 3 cos theta and we can write 3 sine theta. So that would be fine in terms of moving over to a single variable, but I would say it's a bit more conventional to call our parameter t as opposed to theta. So if you prefer, you could write 3 cos t and 3 sine t. But whatever you decide to call your parameter, it's important to give the range of values for the parameter. So in this context, t is our angle, and if we're just trying to capture the part of the circle in the second quadrant, then we need angles from pi over 2 to pi. And there we have a way of describing all those points on that circle of radius 3 in the second quadrant, now using just a single parameter. So I want to make 3 comments that I think will be helpful when it comes to parametrizing curves. First thought is that when you're parametrizing a curve, the path you take matters. So for example, if someone asks you to parametrize, say, the second quadrant portion of a circle, like we did in our part C above, and we want to describe all these points here along that circle, then you have to actually travel along that circle. You would not, for example, be allowed to use the straight line segment that travels from one point to the other. So you have to actually capture the correct set of points when you're doing your parametrization. Line segments are parametrized one way, curves of the form y equal f of x are parametrized another way, and then when it comes to parametrizing circles, we've got a third process. So we just want to make sure we're capturing the right set of points. Second comment is that the choice of parametrization is not unique. So to understand this, I want to flash back to that straight line segment example that we did in part A, and I'm going to write down again the parametrization that we chose. So we said x was equal to 1 plus 6t, y was 2 minus 8t, and z was 3 plus 2t, where t was ranging between 0 and 1. So as you write down that parametrization, you are definitely capturing all the points along this straight line segment that was starting at 1, 2, 3, and that was finishing at 7, negative 6, 5. Okay, now you could think of this parameter t as representing time. And so if you think of it in this context, this parametrization would correspond to, say, running along this line segment in 1 second. Now another person could come along and say, okay, well, I don't feel like running along this line segment in 1 second. I would prefer to run a little slower and actually travel along that line segment over the course of 2 seconds. So they could let t vary between 0 and 2, but that would have a consequence on the way that we write down x, y, and z. So we'd still be starting at the coordinates 1, 2, 3. But if we want to have a total change of, say, 6 in our x coordinate, that would be like having a change of 3 units every second. So we could write 1 plus 3t. And by the time we get to t equal 2, that would still put us over at x equals 7. So basically, if we divide each of these numbers here by 2, that would give us an amount of change that we would expect to see each second. And so we could write things like y equal 2 minus 4t z equal 3 plus t. And you can check that by the time we get to t equal 2, sure enough, we are at 7, -6, and 5. So this is also a correct parametrization. They're both correct. So we've got some freedom here to choose what t values we want to range over, and then to figure out the values of x, y, and z that correspond to those t values. But I would say that if you're looking for just one solid way to do it, this is probably the most standard, because it's just nice to have the t values range between 0 and 1. Third and final idea about parametrizing curves is that the direction along the curve sometimes matters. So let's try to figure out when the direction along the curve matters and when it doesn't. Well, the difference really comes down to what type of line integral you're trying to compute. If you're doing a line integral with respect to arc length, where you're integrating along some curve and you've got a function like f ds, then direction along C doesn't matter. Whereas if you've got a line integral with respect to coordinates, where we're integrating along C, some function that looks like p dx plus q dy plus r dz, which we'll see more details about that in an upcoming video, then the direction along C does matter. So if your differential is a ds, direction doesn't matter, whereas if you see either a dx, dy, dz, or some combination of those, then direction along C does matter. It doesn't matter if we choose a parametrization that goes this way or a parametrization that goes the other way, we'll end up with the same value in either case.